Okay, so what in the world do twitching frog legs have to do with the battery in your phone? I know, it sounds completely bizarre, right? But that's exactly where the story of all of our modern power begins. We're going to trace this really wild scientific journey from a kind of shocking discovery back in the 1700s all the way to the tech that, literally runs our world.
It really does sound like a riddle, doesn't it? Well, the answer is pretty incredible. It lies at the very origin of the battery itself, and it kicked off a scientific rivalry that would change everything, forever.
All right, let's jump in a time machine and go back to the 1790s. So the world of science was just buzzing with all these new ideas about electricity. The problem was, it was totally unpredictable. It was like trying to catch lightning in a bottle. Nobody had figured out how to create a steady, reliable source of it. That is, until someone made a very, very strange observation.
So there's this Italian physician, Luigi Galvani, and he makes this completely accidental discovery. He notices that when he touches a frog's leg with two different metals, say a copper hook and an iron scalpel, the leg twitches like it's still alive. It's wild. So his theory was, aha, animals must generate their own special kind of electricity. But not so fast. Another scientist, Alessandro Volta, he was pretty skeptical. He had a hunch that the frog leg wasn't the source of the electricity, it was just conducting it. He came up with this pretty radical idea for the time. The electricity was actually coming from the two different metals themselves, and the moist frog leg was just completing the circuit.
And just like that, the scientific debate was on. Was it animal electricity or metallic electricity? So to prove his theory once and for all, Volta heads into his lab. In 1800, he comes out with something incredible. A stack of zinc and copper discs, separated by little pieces of cloth soaked in salt water. He called it the voltaic pile, and it produced a steady, continuous electric current. It was, without a doubt, the world's first battery, and it totally settled the argument.
You see, Volta's invention was an absolute game changer because it was based on this fundamental principle of chemistry. And to really get how our modern batteries work, we need to look inside that first invention and break down its basic building block, what we call the voltaic cell.
Okay, I know this diagram looks way more complicated than Volta's simple stack of coins, but trust me, the core principle is exactly the same. This is a modern voltaic cell. You can see it's split into two sides, right? We call those half cells. In each half cell, you've got a strip of metal, that's the electrode, and it's sitting in a solution. These two sides are then connected by a wire up top, and that thing in the middle is called a salt bridge. Let's break down what each of these parts actually does.
First up, let's look at the anode. This is the negative electrode. The easiest way to think about it is as the starting line for the electricity. It's where a chemical reaction called oxidation happens, which basically just means the metal of the anode is literally giving away or losing its electrons. So naturally, those electrons have to go somewhere, and their destination is the cathode, the positive electrode. Over here, a different reaction, called reduction, takes place, and this is where ions in the solution gain those incoming electrons. So remember, electrons always flow from the anode to the cathode. But what about that weird piece in the middle, the salt bridge? Okay, this part is absolutely crucial. It's the little connector that makes the whole thing work. See, without it, the anode side would get super positive and the cathode side would get super negative really fast, and that would just stop the flow of electrons completely. The salt bridge is kind of like a traffic cop. It lets ions flow between the two sides to keep everything electrically balanced so the current can keep on flowing.
So we've seen all the parts, but what's the invisible process that's actually making the power? Let's trace the journey of a single electron as it moves through this little chemical engine.
Okay, let's walk through it step by step. First, over at the anode, the zinc atoms start losing electrons. That's our oxidation. Second, those newly freed electrons jump onto the wire and start traveling. That's our electric current. Third, they arrive at the copper cathode and are scooped up by copper ions in the solution. That's reduction. And finally, step 4. The whole time, the salt bridge is doing its job, releasing ions to balance out the charge on both sides, which lets the whole process run continuously.
Now, trying to remember which is which, oxidation or reduction, can be a little tricky. So here's a super simple mnemonic that chemists use all the time. Oil rig. Oxidation is loss of electrons, reduction is gain of electrons. It's a really, really helpful way to keep it all straight. So all this brings us to a really logical question. We know the electrons flow from the zinc anode to the copper cathode, but why? I mean, what makes the zinc so generous with its electrons in the first place? This is the fundamental question of all battery chemistry. Why does this reaction just spontaneously go in one direction? Well, it turns out it's not random at all. It all comes down to the inherent properties of the metals themselves.
And the answer is right here in this chart. Every metal has this property called standard reduction potential, which is really just a fancy way of scoring how badly it wants to gain electrons. So as you can see, copper has a positive score. It really wants to gain electrons. Zinc, on the other hand, has a negative score. It's much happier giving its electrons away. So when you connect them, it's always a one-way street. The zinc will always give its electrons to the more electron-hungry copper. It's just chemistry.
All right, so let's connect all of this back to the real world. How do these principles from Volta's simple pile of metal disks apply to the batteries that we use every single day?
Well, modern batteries are pretty much divided into two main types. You've got primary cells, like the ones in your TV remote. They're single use. The chemical reaction that makes the electricity only goes in one direction. Once the chemicals are all used up, that's it. The battery's done. But then you have secondary cells. These are your rechargeable batteries. And the key difference is that their chemical reaction is reversible. You can apply an external current, by plugging it into the wall, and force the reaction to run backward, restoring the chemicals for another use.
And you know these guys really well. Those disposable AA or AAA batteries? Those are primary cells. The reaction only runs one way. But the lithium-ion battery in your phone or your laptop? That's a secondary cell. It's a direct, highly advanced descendant of Volta's pile, but it's been engineered so that plugging it in forces that chemical reaction to run in reverse, getting it all ready for you to use again.
So when you think about it, it's an absolutely incredible journey. The exact same basic principle that made a frog's leg twitch over 200 years ago, that controlled flow of electrons between two different materials, is what's powering your smartphone right now. From a simple stack of metal disks to these complex lithium-ion cells in our pockets, it all comes down to that basic chemistry. Which really makes you wonder, what will the next battery revolution look like?